Colligative properties. How solutes affect the properties of solutions. So what determines a colligative property anyway? That usually depends on the concentration, actually, the concentration of the solute particles themselves. So some colligative properties are things like vapor pressure or boiling point or freezing point depression. These are colligative properties that we use in terms of measurement. So what is vapor pressure? Well, there's a pressure or there's a force per unit area where the gas molecules inside of the container, when the container is capped, they're exerting a force on the interior walls of the container. We call that vapor pressure. The vapor inside of the container is exerting a pressure against the interior walls of the container. And we can measure this. And so how does adding a solute affect vapor pressure? It's basically going to lower vapor pressure. That's because the solute solvent particles are more affected to each other, and therefore their less solvent particles are going to evaporate. Less evaporate, then there are less gas molecules exerting pressure on the container, hence that is actually lowering vapor pressure. So if we're going from pure water and then we add a substance to it, we add a solute, then we're going to create this attraction between the solute solvent particles inside of the liquid, and so less of them are going to come out into gaseous form, less of them are going to evaporate, and therefore less particles colliding against the interior walls of the container equals less pressure. So perhaps this might give you an idea. Pure water, right, is the molecules that are right here next to the air are freely coming in and out of solution. And when they do that, they're just bumping up against the walls of the container. If I add a solute, then I have now attractive forces between the particles of water and interacting with the solute. And so less is going to come out of the actual liquid and bump against the wall of the container. Hence, it'll have lower vapor pressure. So how does adding a solute affect the freezing point of the solution? When something freezes, it becomes more ordered, like the crystal lattice starts to form. The molecules tend to line up in that crystal lattice type of structure. And the solute particles, they interfere with that lattice structure forming, so it's more difficult to get it to freeze. So if it's more difficult to get it to freeze, then it lowers the freezing point, making it need a much lower freezing point in order to get the particles to form that lattice structure. To get the particles to slow down, there's now other stuff, solute, in the way, kind of interfering with water molecules aligning. So it has to be much colder, all right, in order to get them to align in that like crystal lattice structure. It's going to require a lower temperature in order to get it to freeze. Hence, lowering the freezing point. Freezing point is the temperature at which the particles become still enough to form that crystalline lattice structure. So here we have a system A and a system B, and the particles in the solid, you can easily shift and move around into the liquid. And so this happens, the freezing point temperature is shown, by the arrows. So when the particles in the solid cannot shift as much equally into that normal freezing point temperature because like the solute is blocking the movement of those particles, then we have a lower freezing point required to kind of get them to hold still in that. It's a really bad way to describe it, but basically like hold still to form that lattice structure. So how does adding the solute affect the boiling point of the solution? These solute solvent particles, they're attracted to each other, right? Because it's dissolving in it. And so it's harder for them to escape as a gas because they like to be together in the liquid. So the boiling point is higher. We're going to require a higher temperature in order to get them to come out of solution because they like being in there together. So where water would just normally freely, you could boil it, and at 100 degrees C, it would escape from that liquid to a gas phase. If we add a solute, you're going to require a higher temperature, more energy to get it to get away from the solute particles there and leave and go into a gas. So here we have boiling point where water, if you can imagine, we have a system A, it's just, being heated. These water molecules are just woo, they're just leaving at their normal temperature. But if I add, solvent to it, then there's still an attraction amongst these particles like this. And so we're going to require a higher temperature in order to boil, hence requiring a higher boiling point for systems that are solute-solvent related. So does the type of solute affect how much change there is? Well, ionic solutes, they're going to produce like 2 or more ions in the solution, and so they affect the colligative properties pretty much, proportionately, meaning more so than actual molecular solutes. Molecular, if you remember, those are things like sugar. They don't ionize, they don't come apart in water, where an ionically bonded salt, for example, comes apart in water. So they're going to affect it proportionally to the number of particles that are actually in the solute in whatever solution we're talking about. And the influence of the solute really depends only on the number of particles when we're talking about the ionic. But molecular and ionic compounds, they're going to produce a different number of particles per mole of substance. So 1 mole of a molecular solid is going to produce 1 mole of particles. But 1 mole of sodium chloride, for instance, is going to produce 2 moles of particles. 1 mole of calcium chloride is going to produce 3 moles of particles. Because this guy right here, remember, he's coming apart into sodium and chlorine because he's ionically bonded, so he's going to produce 2 moles of particles. Calcium chloride, that's a metal and a nonmetal, also ionically bonded, so it's going to come apart as calcium, chlorine, and chlorine. Hence where the proportionality part of this comes from when they're coming apart. Molecular solids, regardless of whatever it is, if it's C6H12O6, if we put glucose, which is covalently bonded, into a solution, it doesn't come apart, so you're only going to get 1 mole of particles. So the more pieces it comes apart in, the more moles of particles it's going to come in, and that's how it's going to affect all the colligative properties of that solution. So if we're going to look at some examples here, how many particles in each of these are going to be given up when we try to dissolve something. This magnesium chloride is going to come into 3. You're going to have 3 moles, right, of particles. Al2O3, that is also ionically bonded. That's the metal, and that's a nonmetal, so we're going to get 5 particles. This is a molecularly bonded compound. That's a non-molar, a non-metal and a non-metal, and so we're only going to have 1, and then of course glucose, as I used as an example before, we're just going to have 1. So this guy right here, he's going to cause the most change in colligative properties because he's going to come up with the most moles of items when he's dissolved inside of water, for example. So in chemistry, we're going to probably ask students to rank compounds, in order of who's going to have the highest vapor pressure to who's going to have the lowest vapor pressure or boiling point. And that's what you'll be doing. So let's just do that for these guys right here. Let's just rank them and who has the highest boiling point to the lowest boiling point. So my highest to my lowest boiling point. Okay. So the more particles, the more difficult it's going to be to get them to leave solution or break those molecular forces between the solute and the solvent. So the guy that's got the most particles, he's going to have the highest boiling point. He's going to require the highest temperature to boil. And they'll go down from there. So this next one is going to be magnesium chloride because it's coming apart into 3 pieces. All right, now we have these 2. So these 2 right here are both covalently bonded compounds. So when it comes to these covalently bonded guys, the guys with the highest IMFs are going to have the higher boiling points. And if you remember IMFs, when we ranked those before, we're looking at the covalent compounds that have, we're looking at their polarity. Are they London dispersion forces? Do they demonstrate dipole-dipole forces? And in our case right here, this guy, this is CH4 methanol, has it's non-polar, right? It's got this positive, so it has London dispersion forces. And London dispersion forces are weakest. So this guy right here, glucose, has stronger IMFs, therefore it's going to have a higher boiling point because it has higher IMFs, and then CH4 would be last. And that's colligative properties, or as I had some professors say it, colligative properties. But I'm country, so I say colligative.